In the previous lectures on Klein-Gordon equation, we have discussed in very detail, first of all, this Kg equation in the covariant form. You have also seen the difficulties with this Kg equation, and after that we have discussed the non-relativistic form of this Kg equation. In fact, when the non-relativistic condition was applied, then one of the problems that the probability density which comes out to be unphysical in case of the Kg equation was actually solved, that this probability density expression becomes simply the expression which we have obtained in case of the non-relativistic quantum mechanics of Schrodinger's quantum mechanics. Now we are going to see a very important problem regarding this Klein-Gordon equation. Actually, in this lecture, our aim is to find the Klein-Gordon equation when a particle is moving in an electromagnetic field. So you can say that this is just Klein-Gordon equation in an electromagnetic field. In fact, this lecture will be divided in two parts. In this first part of the lecture on Kg equation in an electromagnetic field, we will simply discuss two things. First of all, we will find what will be the Kg equation in an electromagnetic field, and then we will see the non-relativistic limit of this Kg equation in an electromagnetic field. But after this lecture, in the second part of the lecture on Kg equation in an electromagnetic field, we will solve the equation or this very equation, and after the solution you will see a very important concept of fine structure will be developed. So in succession, the second part of this lecture will be also very important. But before that, if you will try to understand both of these concepts in a single lecture, that will be actually a very lengthy lecture. So I have divided it into two parts for your convenience. Now you know that any electromagnetic field is described by in fact two potentials which are called electrodynamic potential. In fact, you can see my video in the playlist of electromagnetic theory, or you can say the classical electrodynamics of my playlist, and where you will find a detailed discussion on the electrodynamic potentials. You know, there are two electrodynamic potentials. The first one is called vector potential. This is denoted by the symbol A, and the second potential is actually called a scalar potential denoted by the symbol phi. But when you study the relativistic electrodynamics, then you can see that actually this electrodynamic potential form a 4 vector, and there is also my video on this subject in the playlist of relativistic electrodynamics, where you will get a detailed discussion on the 4 vector potential. So I will suggest you to watch the video on the electrodynamic potential in the playlist of classical electrodynamics. And if you want to know in detail about the 4 vector potential, you can watch my video on the playlist of relativistic electrodynamics, where you will find the detailed discussion on the 4 vector potential. Actually, in terms of 4 vector potential, we denote this electrodynamic potential by the symbol A mu. Actually here this mu is equal to 1 2, 3, and 4. Actually, this A mu represents the 4 components of the 4 vector potential in Minkowski's 4-dimensional space. And this A mu is specified as A1, A2, A3, A4 as usual. You know, any 4 vector is represented like this. Actually, this first 3 components of this 4 vector potential is simply the vector potential A, which you can see here. I have written in this A in the vector form. And the 4th component, A4, is defined by I phi over C. I phi over C. So in brief, you can say that this 4 vector potential is represented as A mu equal to vector A, comma I phi over C, where this A actually represents the 3 Cartesian components of this 4 vector potential, and this 4th one, that is I phi by C, represents its 4th component. Okay. Now you have studied in the playlist of a special theory of relativity of my video on the momentum 4 vector, or it is also called momentum energy 4 vector. You have just studied it a few times earlier. And if you have not watched that video, I will again suggest you to go through the video on the momentum energy 4 vector, or the simply momentum 4 vector, in my channel in the playlist of a special theory of relativity. There you will find a detailed discussion on the momentum 4 vector, and you know this momentum 4 vector is represented as P mu equal to P comma IE over C. Actually, this P actually represents the 3 components P1, P2, P3, or Px, Py, Pz, and this IE over C is the 4th component of this momentum energy 4 vector, or simply the momentum 4 vector. You can compare the representation of this 4 vector potential A mu here and the momentum 4 vector here. You can see that the form of the 4th component of both of these 4 vectors are completely identical. The 4th component of 4 vector potential is I phi over C, while the 4th component of the energy momentum 4 vector is IE over C. Okay. So definitely, as the form of the components of these 2 4 vectors are completely identical, so you can guess that both of these 4 vectors will follow the same transformation law. Okay. And this is the reason that we simply say that this 4 vector potential, or you can say the vector potential A and the scalar potential phi, can be included in the Klein-Gordon equation with momentum and energy. Okay. So how this will be included, you can see this is a very easy concept. Let us consider there is a particle whose charge is equal to E, and this particle is in an electromagnetic field, and that electromagnetic field is specified by the vector potential A and the scalar potential phi. Okay. So in this case, the momentum and the energy of the particle will get modified due to the interaction of the particle with the electromagnetic field. So if the particle is not in an electromagnetic field, then you say that the momentum of the particle is P and its energy is E. But when the particle is in an electromagnetic field characterized by the vector potential A and the scalar potential phi. In fact, in that condition, as I have told you, that there will be an interaction between the field and the particle, and these two quantities, that is the momentum vector P and the energy of the particle, will get modified. So in the presence of electromagnetic field, what will be the momentum and energy of the particle, you can easily see. In fact, this momentum P will now become P minus EA over C. Okay, and the energy E will be now equal to E minus E phi. Okay, so if you want to write the relation between the energy and the momentum in case of relativistic motion, you know the Einstein's famous relation between energy and momentum is given like this. This is E square equal to P square C square plus M square C4. This is Einstein's relation between the energy and momentum of a relativistic particle. Remember, I have told you earlier that I am writing here M, but this M represents actually the rest mass, okay, which is usually denoted by the symbol M0. But here in this series of lecture, we have denoted the rest mass by M, not by M naught, okay. So this is the expression for the relation between the energy E and momentum P of a particle in relativistic motion. Now, since our particle here is in an electromagnetic field, and you have seen that in case when the particle will be in an electromagnetic field, the momentum of the particle will be not P, but it will be P minus EA over C. Okay, and its energy is not now E, but it is E minus E phi. So if you want to write the relation between the energy and momentum of the particle when the particle is in an electromagnetic field, you have to replace this E by E minus E phi, and this P will be replaced by P minus EA over C. Okay, so replacing these two quantities, what will be this result? You can see easily. So instead of E, here I have written E minus E phi whole square, and that is equal to C square P square. So C square is at it, you can see, but instead of P, we will now write P minus EA over C whole square. Okay, and this M square plus C M square times C4 remains at it. Okay, now you can simplify this RHS to some extent. You can take this C as a LCM, and when you will take this C as LCM, the result will be simply CP minus EA whole square, because this C square in the denominator will cancel by this C square in the numerator. So our result is E minus E phi whole square equal to Cp minus Ea whole square plus M square C4. Okay. Now we will write this expression in operator form, and as you know, in quantum mechanics you will know very well that this energy operator is just IH bar del del T, and this momentum operator is minus IH bar del. Del means gradient. Okay. So substituting the corresponding operators of the quantity E and P in this equation number 2, because only these two quantities are observable, so we have defined the two operators. You know that electric charge and this mass, this velocity c, this does not these do not correspond to any operator because they are not observables. Okay, so after substituting the corresponding operators for energy E and momentum P in this equation 2, what will be the result you can see easily. And in fact, we will now write the Kg equation in terms of these operators. So for writing the Kg equation, what you will do? You will simply operate these operators on the wave function psi. So you have to do two things. First of all, replace this E and P by the corresponding operator, and then operate that operator on a wave function psi, which is actually a relativistic wave function. Okay. So you can see the Kg equation now for the particle moving in this electromagnetic field will be like this. E minus E phi was there, but E has been replaced by I h bar del del t minus E phi whole square operated on this function psi, which is actually a relativistic wave function. Mark this. Psi is a relativistic wave function. Okay. And here actually there is in fact yes, yes, see here. Here there is in fact you can see Cp minus Ea whole square. So for P we will now write minus I h bar del and C will be multiplied. So this result will be minus I h bar C del minus Ea whole square plus m square C4 operated on the relativistic wave function psi. Okay. Now you can see we will simplify the LHS and RHS of this equation separately, and then we will substitute these values in equation 3. So you can see the LHS is I h bar del del t minus E phi whole square psi. When you want to find the square of an operator, you have simply to operate this I h bar del del t minus E phi whole square. That means in fact I h bar del del t minus E phi, and this will be actually operated on I h bar del del t minus E phi. Okay. So when we will operate this I h bar del del t minus E phi on I h bar del del t minus E phi, you can see your result will be like this. When this I h bar del del t will be operated on this I h bar del del t, you can see this I square will be minus 1. So I have put here minus. Okay. H bar times H bar will be H square, and when del del t will be operated on del del t, that will be del 2 del t square. Okay. Now this I h bar del del t will be operated on this minus E phi. Okay. E is constant. So this will be minus I E h bar del phi by del t. Okay. And now this minus E phi will be operated on this I h bar del del t, and that will be actually equal to what? This is minus I h bar E del del t. Okay. And when this minus E phi and this minus E phi will be operated on one another, the result will be plus E square phi square. And again, when you will take this I h bar, this minus E phi operated on this I h bar del del t, then again there will be minus I e h bar del phi del t, and so this is here minus 2 I e h bar phi del del t. Okay, and the size that is. Similarly, now we will simplify this. Minus I h bar c del minus E a whole square psi. Again, you have to simplify this result in the similar manner. And when you will operate this operator on itself, the result will be like this. This will be minus h bar square c square del square plus I e h bar c del dot a. Okay, del dot a. Here actually this del and a both are vector, so a squaring means a scalar product, because you know when you write any vector, let us say a square, that means a dot a. Okay, a square of a vector means a dot a. So this will be del dot a, and plus 2 ie h bar c a dot del and e square plus a square operated on psi. So let us now substitute these two values, this value and this value, in equation 3, and so your Kg equation now will become like this. This is just repeated here. You can see this is minus h bar square del 2 by del t square. This term is here, and minus 2 ie h bar phi del del t minus I h bar del phi by del t. You can see it. This is here, and plus e square phi square operated on psi, and that is equal to this much. I have just repeated this term here. I am just giving a reading. As you can see, this is minus h bar square c square del square plus this term has been written first. You can see it here, 2 ie h bar c a dot del and plus ie h bar c del dot a plus e square a square. Okay, and there is also in fact plus m square c4. Okay, m square c4. So m square c4 has been also added here, and then it is operated on psi. Okay, so actually this is the Kg equation for a free particle of charge E in the electromagnetic field. Now you can see in this equation, which is just Klein-Gordon equation for a particle of charge E in an electromagnetic field, there is actually no spin operator present in this equation. Okay, since there is no spin operator present in this equation, so you can guess that the particle about which we are talking here, that the particle of charge E which is in electromagnetic field, definitely that particle will have no spin property, or you can say that the electric and magnetic moment associated with the spin of the particle, it will be not present here. That will be actually 0. So this equation also gives a very important information that this equation is independent of the spin of the particle, and that's why we say that this Klein-Gordon equation is applicable for a particle having 0 spin, no spin. Okay, actually I have mentioned it here. You can see that this form does not contain any Pauli spin operators, and therefore no intrinsic spin dependent magnetic or electric moments are associated with the particle. Okay, described by this Kg equation. So I have told you that since the equation does not contain any spin operator, and so we can easily say that the particle about which we are talking about here will have not any spin dependent property like the magnetic dipole moment or the electric dipole moment associated with the spin will be 0. And that's why we say that this Kg equation is applicable only for those particles which have no spin dependent property. Okay. So this is the kg equation in case of particle in an electromagnetic field. Actually, this equation which we have obtained just now will be solved in the next lecture. You will see that by the method of series we will solve this equation and we will get very beautiful results which will actually explain the fine structure. Okay. But before that, in this lecture, now I would I would try to like the non-relativistic limit of this kg equation. Actually, the kg equation, in kg equation we have seen that the wave function psi is a relativistic wave function. But if your aim is to write down this very equation in a non-relativistic form, so what will be the non-relativistic limit of this kg equation? You can see easily. And for that you have to remember the facts which we have discussed in the earlier lecture. You have seen that the relativistic wave function psi of rt, when you write psi of rt, this is relativistic wave function. This relativistic wave function psi of rt you have learnt in the previous lecture is related to the non-relativistic wave function which I have denoted by the symbol psi prime of rt. This psi prime of rt, you know, it is non-relativistic wave function, and psi of rt is relativistic wave function. And you have learnt in the previous lecture that this relativistic wave function psi of rt is equal to what? This is equal to psi prime of rt times e to the power minus imc square t over h bar. You can remember this. I have actually derived this relation in the previous lecture, and here I am writing it directly because you have learnt it very well in the previous lecture. Okay. Now simply we have defined this psi of rt in terms of the non-relativistic wave function psi dash of rt. Now, as the kg equation contains the first order partial derivative of this wave function psi, and it also contains the second order partial derivative with respect to t. Okay. So from this relation, first of all we will find what will be the first order time derivative of psi and what will be the second order partial derivative of psi with respect to t. So let us find it. You can see del psi by del t. As you can see, this psi is actually a product of two functions. First function is psi dash of rt. Second function is e to the power minus imc square t over h bar. So following the rule of differentiation of product of two functions, you can easily find what will be del psi by del t. Let us see. First of all, we will differentiate this psi. So this will be del psi by del t. And the second factor remains at each. This is in fact e to the power minus imc square t over h bar. Now, we will keep the first factor psi prime at each, and we will differentiate the second factor e to the power minus mc square t over h bar. So when you will differentiate it with respect to t, what will be your result? You can see this will be e to the power minus imc square t over h bar, and when this minus imc square t over h bar will be differentiated with respect to t, you can see this minus imc square over h bar is a constant factor and del t by del t will be 1. So this is simply minus imc square over h bar. Okay. Now you can see this factor e to the power minus imc square t over h bar is a common factor. It is present in both terms. So let us take this factor as a common factor. You can see it here in the second step. This will be then del psi by del t minus IMC square over h bar times psi dashed at times e to the power minus IMC square t over h bar. So this is the value of first order derivative of psi with respect to t. Remember, psi is the relativistic wave function and psi prime is the non-relativistic wave function. Remember. Now, again we will differentiate this del psi by del t with respect to t, then we will get del 2 psi by del t square. See here, again there are two factors. First one is written here in this bracket. You can see this is del psi by del t minus IMC square over h bar psi dash. And the second factor is outside of the bracket. This is e to the power minus IMC square t over h bar. So when we will differentiate the product of these two functions, what will be the result? You can easily see. See this. After again differentiating, this is del 2 psi by del t square. First of all, I have differentiated the factor inside the bracket. You have seen that inside the bracket the first term was del psi prime by del t. And when it will be differentiated, this will be del 2 psi prime by del t square. And minus the second factor you can see is what? This is IMC square by h bar times psi dashed. IMC square over h bar, this is a constant factor. So it will remain at ease and this psi prime will be differentiated. So this will be del psi prime by del t. So you can see I have written it here. This is minus IMC square times del psi prime by del t. And the factor outside of the bracket remains at ease. Okay. Now we will keep the factor inside the bracket at ease. So you can see this has been written here directly. This is del psi prime by del t minus IMC square over h bar times psi dashed. And this factor outside of the bracket will be now differentiated with respect to t. So what will be the result? You can see this will be e to the power minus IMC square t over h bar times minus IMC square over h bar, because del t by del t will be equal to 1. Okay. Now rearrange the term in RHS. You can see this factor e to the power minus IMC square over IMC square t over h bar is again a common factor. So I have taken it outside of the bracket, you can see, as a common factor. Now the remaining terms will be what? This is del 2 psi by del t square, del 2 psi prime by del t square. So this is here. Okay. And again this second term minus IMC square over h bar del psi prime by del t. This has been written here. You can see. And now this del psi prime by del t and times this much minus IMC square over h bar. Okay. So this will be minus IMC square over h bar del psi prime by del t. Okay. And this term minus IMC square over h bar times psi dashed at times minus IMC square over h bar. When these two will be multiplied, you can see this minus will become plus, but I times I, that will be I square, and that will be again minus. And this m is into m, that will be m square, c square into c square, that will be c4, h bar times h bar, that will be h bar square times psi dashed. Okay. Now you can see the second term here and the third term, both are equal and sign of both are minus. So this result will be del 2 psi by del t square equal to del 2 psi prime by del t square minus 2imc square over h bar times del psi prime by del t. Okay, and then the last term, this is minus m square c4 over h bar square times psi dashed, and this e to the power minus imc square t over h bar is just a common factor. Okay, so we have obtained the value of del 2 psi prime by del t square, and also you have calculated the value of del psi by del t. Okay, the page has been turned, but this will be just okay. You can see actually when there is a larger time, this device is this device actually stop its working. Now this del psi by del t and del 2 psi by del t square. Now these two values will be substituted here in this equation number A, which is actually the Klein-Gordon equation. You can see in LHS there is the term minus h bar square del 2 del t square psi. So this del 2 psi by del t square will be is the first term, and instead of this del 2 psi by del t square, we will substitute the value which we have obtained here. Okay, so you can see I have substituted this, since minus h bar square is a common factor there, so that will be minus h bar square del 2 psi prime by del t square. See it here, and since there is minus sign as a common factor, so sign will be just changed, plus, see here this term, this minus minus will now become plus, so plus 2imc square h bar del psi prime by del t. Again there is minus m square c4 by h bar square psi dashed, so minus minus will be again plus, so this is m square c4 psi dashed, because by this minus h bar square it is in fact multiplied. Okay, now the second term in this equation is what? You can see the second term is minus 2ie h bar phi del by del t. Okay, and when this will be operated on psi, this will be del psi by del t. In second term, del psi by del t is present, and you have obtained the value of del psi by del t here. You can see, so this value will be substituted at that place. So after substituting that value, you will see this is in fact minus ie h bar del phi by del t psi prime minus 2ie h bar phi del psi prime by del t. Okay, and minus 2mc square e phi psi prime plus e square phi square psi prime, and this is e to the power minus imc square t by h bar. This is a common factor. Okay, now see the RHS. RHS of this equation is this much. This is the RHS, and in RHS neither del psi by del t nor del 2 psi by del t is present. So this RHS will remain at each, and you can directly write the RHS of this equation. But only there will be one change, as in that equation psi is present, but psi has been defined like this: psi is equal to psi dashed times e to the power minus imc square t. So psi will be only replaced in RHS by this factor psi prime times e to the power this much. So instead of psi, there will be psi dashed, and this factor will be multiplied. Okay. So simplification of RSH is much easy. This operator remains exactly same as that this was in the equation 1, sorry A, but in outside of the bracket there was psi, but psi is now equal to psi dashed e to the power minus IMC square T over H bar. Okay. Now you can see this factor e to the power minus mc square over t, sorry, e to the power minus imc square t over h bar is present both in LHS and RHS as a common factor. So that will cancel out. Okay. And apart from that, there will be some common terms, and that will be also cancel out. What is that common term? You can see this term m square c4 psi dashed. Okay. And here also there is m square c4 psi dashed. That will be also cancel out. Okay. And so cancelling this common factor e to the power minus imc square t by h bar and this m square c4 divide m square c4 times s dashed, and at the same time we divide this equation both sides by the factor 2mc square. So these three algebra you have to do it here. First of all, cancel the common factor e to the power minus mc square t by h bar, and also this m square c4 side dashed is present in both sides. So these will be also cancel out. And after that, you have to divide this equation in both sides by this factor 2mc square. So doing all these algebras, you will get this result. This result will be minus h bar square over 2mc square del 2 psi prime by del t square plus I h bar del psi prime by del t. You can do the algebra, and minus I e h bar over 2mc square del phi by del t psi prime, and minus I c h bar phi over mc square del psi prime by del t, and minus e phi psi prime plus e square phi square psi prime over 2mc square. And in RHS, the remaining terms are minus h bar square over 2m del square plus I e h bar by 2mc del dot a plus I e h bar by mc a dot del and plus a square over 2mc square operated on psi. Okay. Now you know, if we consider the relativistic limit. In fact, in a relativistic limit, you know that the energy of the particle, which we denote by the symbol E dash, this is much smaller than the rest mass energy mc square. Or in other words, you can also say that this mc square is much greater than E dashed. Okay? If we consider the non-relativistic energy. So this non-relativistic energy E dashed is much smaller than the rest mass energy. So all the terms containing in this above result, which has a factor 1 by mc square as a factor, that can be neglected, because this 1 over mc square will be very small, and so we will neglect all those terms containing 1 over mc square as a factor. Actually, I have mentioned it here. You can see, considering mc square is much greater than E dashed, which is non-relativistic energy, and mc square is also very, very greater than E phi. In that condition, the terms of order 1 over mc square will be neglected as compared to E dashed and E phi. Okay. So after neglecting all those terms, this equation will now become very simple. You can see in LHS, this term will be neglected because here mc square is present. This term will be also, I am just crossing the terms which will be neglected. This term also contains mc square in denominator. This will be also neglected. This term also contains mc square in denominator. This will be also neglected. And this term also contains mc square in denominator. So this will be also neglected. So, and this E phi term, E phi, it is also very small because I have considered that this mc square is much greater than E phi. So, in fact, in LHS, neglecting all the terms which is very small, only one term will remain, and that term is, in fact, which is I am just ticking here. You can see this is I h bar del psi prime by del t. Okay, del psi prime by del t. So in LHS there is I h bar del psi prime by del t. Okay, and here you can see in RHS the term is minus h bar square over 2m del square, and this term I e h bar over 2mc del dot a plus I e h bar mc times a dot del, and this term contains again mc square in denominator, so this will be neglected. Right? And in LHS there is minus E phi psi prime. When you will bring this this minus E phi psi prime in RHS, this will become plus. So we will write this term minus E phi psi prime in RHS. And then what will be our result? You can see easily. In LHS there is only IH prime del psi prime by del t, and in RHS you can see this is minus h bar square over 2m del square plus IE h bar over 2mc del dot a plus I h bar over mc a dot del, and plus this e square a square over 2mc square plus, and this term may also be neglected. I am just crossing it. You can see that this term can be neglected because it is very small. Okay. So this equation you can see this is just in the form of I h bar del psi prime by del t, and this is equal to E psi. E psi or E psi prime, or you can say that this is H psi prime. This is just Schrodinger's time dependent equation, and so we say that this equation which we have obtained here, this is, let us say, A prime, is simply the non-relativistic Schrodinger equation for a particle of charge E moving in an electromagnetic field. Okay, so you can say that this Kg equation in an EM field reduces to a correct non-relativistic limit with appropriate approximation. But you have seen that you have to take so many approximate values. So in this way we can transform the relativistic Kg equation into its non-relativistic equivalent form. Okay. But the more important fact of this lecture is the form of the Kg equation in electromagnetic field, And as I have told you, when we will see the next lecture, then we will start our lecture from here. You can see we will start our lecture with this result, and this result is actually the Klein-Gordon equation for a particle moving in an electromagnetic field, and we will try to solve this equation when the particle will be just in a Coulomb field. When the particle will be in a Coulomb field, then we will try to solve this equation, and you will see that actually the solution will be in terms of the power series, and in terms of power series we will solve the equation, and from that solution we will get so many important results among and one of the important results will deal with the fine structure. Okay, so this is all about the Klein-Gordon equation in an electromagnetic field. I hope you have understand the concept very clearly. So watch the video seriously, write down these things in your notebook, and then you will see when you will revise from this concept from your notebook, everything will be crystal clear to you. Okay, so thank you very much for watching and supporting me.